Assignment Astrophysics and Cosmology. We'll start with question 17 from this assignment. In question 17, explain how the light emitted from the star enable us to determine the temperature of the star, hence its luminosity. Like the light which is coming out from the star, using that light, how we can determine what's the temperature of the star, and using that, how we can work out the luminosity of the star is. It's So the basic concept you just have, as we apply the black body laws on the star, like the Wien's displacement and the Stephen Boltzmann law. So first, when we receive the radiation from the star, we'll determine the lambda max. What is the meaning of the term lambda max? Lambda max does not mean the maximum wavelength of the radiation. Lambda max means it's a wavelength for which intensity is maximum. So the wavelength which maximum intensity is there, we call that as a lambda max. So first, the radiation which we receive from the star, we determine the lambda max from the spectrum which we obtain from the star. And then we know that according to the Wien's law, the product of a lambda max and a temperature is constant, 2.8 and exponent minus 3. So if we know the lambda max, we can just divide it by the constant divided by lambda max. What we'll know the temperature of the star. And how we can determine the luminosity of the star using a Hertzsprung and Russell diagram. So once we determine the temperature, the luminosity of the star is compared to that of a sun, and we have a temperature, and the scale is like, if this is 24,000, this will be 12,000, this will be 6,000, this will be 3,000. So the temperature of the star, using the temperature of the star, we can determine its luminosity using the HR diagram. So simply what we did, we recorded the spectrum of the star. From this spectrum, we determine the lambda max. Lambda max does not mean the maximum wavelength which the star is emitting out. Lambda max means it's a temperature, it's an intensity at which the wavelength is maximum. Like most of the radiation are in this order. And then using the wavelength, we can use the Wien's law. According to the Wien's displacement law, lambda max and T is always constant. So we can determine the temperature of the star. And from temperature of the star, we'll use a HR diagram, Hertzsprung-Russell diagram, which is a graph between the temperature and the luminosity. So we can determine, usually when the temperature is low, the star have low luminosity as compared to that of a high temperature. And here we find the red giants, here we find the white dwarfs, and the supergiants are also there. Is it clear? Discussion part A. The next is, so this is always the case. That's how the astrophysicists determine the temperature as well as the luminosity of this star. Then an object whose luminosity is known may be referred as a standard candle. So what is a standard candle? We consider an object with a known luminosity, that's a standard candle. So we know its power or luminosity. And we have the formula that intensity or the flux is power on unit area. So if an object is there at a distance r, or you can say d, because there will be a lot of points which are at a distance d from the source, so it will always make a sphere. So in that case, intensity will be equals to the power, and area is what? Area is 4 pi r square. So we can use this r is the radius or the distance between the stars and the object. So if we know the power and we know the intensity, we got the intensity, so we can work out the distance of the star. So the question is, explain how standard candles are important to astronomers and outline how standard candles are used to find the distance of the stars, distances of the stars. So how we use a standard candle to determine the distance of the stars? So first thing, as we assume that star is having a known luminosity, means the power. Then we measure the flux or intensity or the brightness of the star. And by using this law, like intensity is power over area. So if I need the distance, distance is r. R is the distance. So if I need, so r square will be equals to p divided by 4 pi. And if I need only r, then I will take a root. So I'll get this. So luminosity or power. Intensity refers to the brightness of the star or the flux of the star. You can refer that as F. You can also refer that as I. So usually you use the term intensity is power or unit area, or the flux is luminosity over area. So for the star, usually we use the term flux and the luminosity rather than power and intensity. Is it clear how we can determine the distance of this star using the standard candle? The astronomers have been watching an old star suddenly stir back into new activity. They are actually studying a star known as Sakurai objects, the old white dwarf that has run out of hydrogen of nuclear fusion in its core. Astronomers now believe that some such stars can undergo a final burst of a fusion. Because usually, what happened, how the star reaches this white dwarf, first it will be a protostar, then it turn into a main sequence star, then it will turn into a red giant, then a planetary nebula, which eventually turn the central core into a white dwarf and eventually into a black dwarf. But they're saying when it is a white dwarf, some still fuel is left to undergo a fusion, so it can undergo a fusion. Computer simulation indicate that convection would bring the hydrogen in from the outer region of the star and cause the flash of a nuclear fusion. Like we have a core is there, then some hydrogen is in the surrounding. So because of the fusion, the hydrogen come closer and it will undergo a fusion again. This produces a sudden increase in the size and the brightness of the star. The HR diagram is shown here, Hertzsprung-Russell diagram, which is the relative luminosity. Relative luminosity, it's actually a comparison of a luminosity with sun. When we say luminosity is 1, it means like it is same as the sun. And we have the temperature. We have the temperature for 40,000, 20,000, 10,000, 5,000, 2,000. So in a HR diagram, the temperature are always divided by 2. Like you can see 40,000, 20,000, 20,000, 10,000, 10,000, 5,000, 5,000, 2,000, 500. On the diagram, mark a likely position of an object before the final burst of a fusion take place and label this as X. So basically before the final burst, so before the final burst is a white dwarf. And what is the position of the white dwarf? The white dwarfs have a very low luminosity, but they have a relatively high temperature. So here you can mention X. That is the region where we can find the white dwarf. Then on the diagram, mark a likely position of an object during a final burst. If you see in the final burst, the size also increases. The final burst is there. As a result, the size and the brightness increases. So what is Y here? Because it will be a red giant. So this is a red giant. Why we label here? Then we have question 19. A massive planet orbits the red dwarf Gliese 876. The planet was discovered after the wavelength shift in the spectral lines were seen in the light received from the star. Explain how a massive planet orbiting the star can cause a change in the wavelength of a light received from the star. So, how there is a change in the wavelength? This is related to a redshift. So, as a result, what will happen? So, a massive planet orbit the red dwarf star. So, this let's say this is a red dwarf star. Okay, and there's a massive planet, but the size of a planet will be smaller as compared to that. So let's say this is a massive planet. The planet was discovered after a wavelength shift in a spectral lines were seen. So we observe that the wavelength, because a star is what is emitting out the radiation. So we observe the wavelength which we expect to receive from the star and wavelength which we receive, they are not same. That's a Doppler shift. For example, let's say the wavelength is 400 nanometer, but what we receive, we might receive different wavelength, longer or shorter. Explain how a massive planet orbiting a star can cause a change in the wavelength. Look, when the massive planet is orbiting the star, the massive planet will have a gravitation, like massive planet will also have a gravity. As a result, how do we know actual wavelength? How we don't know actual wavelength? Because every element is having a unique spectral line. So when we compare, because we know the most of the matter which is present in the star is hydrogen and helium. So we have these wavelengths, we have the line spectrum of the star, and we compare this line spectrum of the star, like receiving from the star, with the one in the lab. For example, this is done in the lab, the hydrogen spectrum, and the one we receive from the star. So this is what we receive from the star. So if we found that the wavelength appear to increase, means it is moving away. If the wavelength is decreasing, it means it is moving towards. So as a result of the gravitational attraction, as a result of the gravitational attraction, the particles start to move. When these particles start to move, because the massive planet is exerting a gravity, star is pulling the planet. That's why, and the planet is moving, which is like a centripetal force is there. That's why the balance is by moving around. But as a result, the velocity of the star, relative velocity of the star, or the particles which are present in the star, they will experience the gravity, so they start to move towards the planet. when these particles in the star move toward the planet, so maybe the wavelength which no it should emit out like hydrogen, it should be 400 nanometer. But what we receive, it appeared to be different than what we expect. So that indicate that there's a motion in the star or the movement in the star. That's how it is causing a change in the wavelength. So how to structure this answer? How you write the answer? First thing you'll mention that as a massive planet is orbiting the star, and there's a gravitational force between the star and the planet, and the gravitational force of the planet on the star causing the particles of the star to move. As a result, we'll observe a change in wavelength or a Doppler shift. Is it clear? But if a small planet would have the same, because the small planets will have a weaker gravity. The gravitational force, the smaller planets will be there, but because they have a weaker gravity, so there's a gravitational force of the star which is not letting these particles to move away easily. But if there's a massive planet, then this effect is more prominent as compared to a minor planets. The minor planets have gravitational force but very weak as compared to massive. Next is the maximum shift in the spectral line of a wavelength is 4.35 exponent 7 meters receive from a gliese which is 3.19 exponent minus 13. Calculate the maximum velocity away from the earth. So if it is maximum velocity is moving away, means the wavelength should increase. So first we determine the Doppler shift. How to determine the Doppler shift? The Doppler shift is the change in wavelength divided by original wavelength, which is Z. So change in wavelength divided by original wavelength. In the question they mentioned the maximum shift in the spectral line of a wavelength received from is this is the maximum shift. Like this is the change in the wavelength which we observe. So the change in wavelength is 3.19 into 10 to the power minus 13 divided by the original wavelength. What we expect to receive 4.35 exponent 7. This will give us a Doppler shift. And after getting a Doppler shift, the formula is the Doppler shift is the speed of a object divided by speed of a light, like speed of the star. So just the Doppler shift multiplied by speed of a light. So after getting Z, I will multiply by speed of a light, which is 3 into 10 to the power 8. So this will give us the speed at which it is moving. Is it clear, this one? How to work out the speed of the galaxies or the stars? Shouldn't the change be the subtraction of the two? Yeah, it's given already. They gave us the change in the wavelength. They did not say the new wavelength. What they give here, they say the maximum shift. Maximum shift means the change in the wavelength. So the maximum shift in the spectral line, they did not say that first we expect to receive 4.35 exponent minus 7, and now we are receiving 3.19 into 10 to the power minus 13. That is not the case. What they mention here clearly in the question that the maximum shift, like the change is given here. This is the change, not the new wavelength. This is delta lambda. If they said like example expected is this and now we are receiving this, then yes, we will take a difference in this wavelength divided by original wavelength. The mean intensity of a solar radiation arriving at the Earth is 1.37 kilowatt per meter square. The distance of the Earth from the Sun is 1.5 exponent 11 meter. Show that the luminosity of the Sun is about 4 exponent 26 watt. So if you want a luminosity, what is the formula for the luminosity? Luminosity is basically, if you need the distance, we have the formula that the flux is equals to luminosity over area. It's the same formula as the intensity is power divided by area. Okay, so flux is luminosity over area. So if we have the source is there and we are at a distance d from the source, we want to determine, because it will always make a sphere. So in this example, let's say this is a sun, and here we have Earth, and the distance between the sun and the Earth it's 1.5, which is also called 1 astronomical unit, 1.5 exponent 11 meter. That is the distance. So if we want to show the luminosities about this, so luminosity will be flux times the area. Flux, this is a flux, watt per meter square, or intensity, which is 1.37 into 10 to the power 3. What about the area? Area is equals to pi r square, 4 pi r square. Why 4 pi r square? Because it's not like only one point. Whenever, remember, just recall the formula for intensity. It is always calculated for area, not for point. So there will be lot of points which are at a distance of 1.5 exponent 11. So in short, what we will have the total area, which is 4 pi r square. So we just substitute 4 pi, which is 3.14, and r square. R is a distance here. In this case, it will be 1.5 into 10 to the power 11 square. So that will give us the luminosity. Is it clear, this one? Luminosity or the power is having the same meaning, and flux, intensity or the brightness is having the same meaning, which is 3.87 exponent 26. Okay. So this will be 3.87 exponent 26 and unit will be watt, because luminosity is a power. The energy radiation from the sun result in a decrease in the mass of the sun. Calculate the decrease in mass of a sun due to a radiation over a period of 1 year. We want to find that, like, this energy radiated from the sun, as the sun is emitting out energy, the mass of the sun is decreasing. We want to work out how much mass of a sun is decreasing for 1 year. And we know the power of the sun, like the previous one, the luminosity of a sun, we know. We just calculated that this is a luminosity 3.87 exponent 26, which is about 4 exponent 4. So according to Einstein equation, E is equals to mc square. So if I need the mass, it will be energy divided by c square. And if I need energy, like power is energy divided by time, so energy is power multiplied by time. So power multiplied by time divided by c square will be equals to m, where p is the power. How much is the power? So the power is the same thing what we got the luminosity, 3.87 exponent 26. In 1 year, how much energy it will emit out? That is the time interval. So 3.1 exponent 7, that's the total time in 1 year, divided by speed of a light square. So 3 exponent 8 square. That will give us how much mass of the sun will decrease. What is the answer here? So you can say change in energy is change in mass into speed of a light square. Like mass and energy can be converted. 1.35 exponent 17. So 1.35 exponent 17 kg. The next is question 21. Al-Nilem and Mintaka are the stars in the constellation Orion. The table gives some information about these stars. You can see the surface temperature, the luminosity, and the distance from the Earth. And L is state where these stars would locate in a HR diagram. Look, in a Hertzsprung-Russell diagram, generally for a Hertzsprung-Russell diagram, we have a luminosity and we have a temperature. So as the temperature of the star decreases, the luminosity will also decrease. If a temperature of a star is high, it will also have a high luminosity. And what is the approximate, like you can compare, because our sun is about, like luminosity we compare as 1, and its temperature is around 6,000 Kelvin, the surface temperature we are talking about. But when you see this one, because it is 10 power 4, so it will be 1, 2, 3, 4. So it will be 27,500. What about this one? This will be about 30,000. Their surface temperature is very high. So likely they will be here on this side. And the luminosity is also, like, as you can see, it's a very high luminosity. So and the distance from so two comparison are there compared to luminosity, like their luminosity compared to that of sun. It's a very high luminosity. And their temperature is also high. So where we expect them with a high luminosity and a high temperature, because here we have a high temperature and here we have a low temperature. So we expect these stars to be here, somewhat here. So where these stars would be located in a HR diagram, Hertzsprung-Russell diagram. So we expect that these stars will be like on the top of the main sequence, not the main sequence one, because usually on this region we expect like top of the main sequence, because they have a very high luminosity compared to their temperatures as well. Or you can also say top of main sequence, that's also fine. Or you can refer to that they're on the above the main sequence. But it's fine you mention about the main sequence, because it's just a compare. One more question is there. Is it clear? Next is calculate the peak wavelength which radiation calculate the wavelength at which the peak radiation power occur. So peak wavelength, we use a Wien's displacement law. According to a Wien's displacement law, the lambda max, the maximum wavelength which the star emit out, and the temperature, the product, according to a Wien's displacement law, the product is 2.89 into 10 to the power minus 3. That's a Wien displacement law. So if I need the lambda max, I can work out, like I just simply divide by temperature. So lambda max will be equals to 2.89 into 10 to the power minus 3 divided by the temperature, which is in this case, we need for Mintaka, which is 3 exponent 4. So this will be divided by 3 into 10 to the power 4. What's the answer for wavelength in meters? 9.63 exponent 8. Minus 8, yeah. Next is calculate the radius of alnilam. So how we determine the radius? We have the luminosity. Whenever you need the size of the star, you use a Stephen-Boltzmann law. According to Stephen-Boltzmann law, luminosity, or we can also say the power, is equals to sigma, the Stephen-Boltzmann constant, area, the size of a star, and T raised to power 4. So in the question, we have both. We have the luminosity, compare, and we have the surface temperature as well. So we can determine the radius. And it will be, because it's a sphere, so 4 pi r square. So what luminosity is given? 5.3 exponent 5. So we write 5.35 exponent 5. Then this is equal to, and one more thing about the table, because luminosity compared to that of, like, this is a ratio between the luminosity of the star with luminosity of the sun. Like, say, luminosity of alnilam, we are representing AL divided by luminosity of the sun. That answer is 5.37. That answer is 5.37 exponent 5. So if I need the luminosity of this one, I should multiply by luminosity of the sun. So means if I need the total luminosity, because we need the total, so this will be 5.3537 exponent 5 times 3.85 exponent 26. That's why we should multiply both of, because we need the luminosity of that specific star. Then we have a sigma, that's a constant. In exam it will be given. You don't have to memorize. It is 5.67 exponent minus 8. Then area will be the multiply by area, which is a sphere 4 pi r square, times the temperature, which was given already, 2.75 exponent 4 and raised to power 4. So if I just will solve for radius, this whole equation, that will give us a size of this. Is it clear? Then only mathematical calculation is there. Like example, 5.37 exponent 5 times 3.85 exponent 26 divided by 5.67 exponent minus 8 multiply by 4 multiply by pi multiply by 2.75 exponent 4 raised to power 4. That will give us a radius in a root. The size of this star according to the given values. Next is deduce these stars give the lower intensity of a radiation at Earth. Deduce which of these stars will give a lower intensity. So how we can deduce which of the star will give us a lower intensity? We just have to compare the ratio between them. Their distance from the Earth is given. Distance from the Earth is given here. And what is the relation between the intensity and the distance? It is look, the intensity or the flux is a power or luminosity on unit area. And area is because we consider a standard candle known luminosity. So intensity is I over 4 pi r square or d square. D is not a diameter, d is the distance between the source and the observer. So what we can do, because the question is which of these stars give a lower intensity of a radiation to Earth. So what we simply have to do, we have the luminosity of these stars. Like I first we'll solve for luminosity of alnilam. Like how we will solve luminosity of alnilam will be like intensity will be luminosity of alnilam divided by 4 pi d square. D is a distance, which is everything is there. And this luminosity the of alnilam will be multiplied by the luminosity of the sun as well. Like we have 5.37 exponent 5 multiplied by 3.85 exponent 27. So we multiply both of them, so we'll get this value. Okay. And the distance is already known. So we'll get the intensity of the for alnilam. Then we'll find the intensity of Mintaka, like how we work out intense luminosity, which is the power. Again, the power, this will not be 9, it will be 9 into 10 to the power 4 times 3.85 exponent 26. That will be the total divided by 4 pi and d square. D is a distance. So we substitute the distance. So luminosity is there and distance is there. So we will find the intensity of this Mintaka. And then we will compare. You can take a ratio like what is the comparison between them, which is a higher value. Is it clear? Then comparison is always like a ratio. So it's best is once you get the answer for the intensity of the two stars, just divide by the common factor to get the ratio. Like how many times, as you see a night sky, some stars appear to be much brighter than the other, even though they might be far from, they might be very close to us, but not that bright as compared to stars which are far. So intensity which we receive from the star depends on the size of the star, depends on the distance at which the star is from us, and it also depends on the temperature of the star. But the main two factors which affect the brightness is the luminosity, the power, and the distance from us. Is it clear? This the last part of the question.